Welcome to this new activity, which is about the Cobb-Douglas model. So here, we're gonna try to optimize the Cobb-Douglas function given some conditions, given some constraints. So it's a constrained optimization problem. So in this activity, we have that the research department of a manufacturing company arrived to the following Cobb-Douglas production function for a particular product. We have the function n of x and y equals 10 times x to the power of 0.6 times y to the power of 0.4. And in this equation, the x represents the number of units of labor and the y represents the number of units of capital required to produce n of x, y, units of the product. So each unit of labor costs $30 and each unit of capital costs $60. In addition, you have a budget which is limited. So you have just $300,000 which are budgeted for production of the product. So the question is how that amount should be allocated to maximize the production, and we're going to find the maximum production. So we're going to use the Lagrange multipliers method to solve this problem. But first of all, we have to write our problem. So here we have to maximize the objective function, which is the production function n of x and y, equals 10 x to the power of 0.6, y to the power of 0.4, subject to, and we're going to write our condition. Remember that if you produce n, you're going to use x units of labor and y units of capital. Each unit of labor costs $30 and each unit of capital costs $60. So you're going to spend exactly 30x plus 60y dollars. And if the budget is $300,000, so the 30x plus 60y must be equal to the maximum budget, which is $300,000. So this is your constraint. And here you can forget about the text problem and try to solve this. And we're going to solve this using Lagrange multipliers again. So the first step is to write your constraint as g of x and y equals 0. And here, again, you have to move what's on the left to what's on the right to the left side. So we're going to write g of xy equals 30x plus 60y minus 300,000. Second step, construct the Lagrange function, which is capital F of x, y, and lambda equals 10 x to the power of 0.6, y to the power of 0.4, plus lambda times your constraint 30x plus 60y minus the budget 300,000. Okay, now third step, the critical points. And here you have to compute the partial derivatives of the capital F function. Okay, so let's start with fx. Here you have x to the power of 0.6. Its derivative is 0.6 times x to the power of 0.6 minus 1 using the power rule. And 0.6 times 10 is 6, so let's write it 6x to the power of negative 0.4, which is 0.6 minus 1, times y to the power of 0.4. And from the second term, you will get 30 lambda, so plus 30 lambda equals 0. Second equation, which is fy, equals, using the same method, you will get 4x to the power of 0.6, y to the power of negative 0.6 plus 60 lambda equals 0. And the third quantity, which is f lambda, which is equal to 30x, your constraint, 30x plus 60y minus 300,000. To solve this system, I will show you a universal method, which works with the Cobb-Douglas functions. So the strategy here is to get the lambda from the first equation, get the lambda from the second equation, write the equality between the two quantities, and insert the relationship in the third equation. Okay, so let's do it. First, second, third equation. From the first equation, we'll get that lambda equals negative 6x to the power of negative 0.4, y to the power of 0.4 over 30. From the second equation, we'll get lambda equals negative 4x to the power of 0.6, y to the power of negative 0.6 over 60. Now we can, of course, simplify these expressions. So let's write it negative x to the power of negative 0.4, y to the power of 0.4 over 5, because we can cancel the 6 in the numerator and in the denominator. And here we can write it as negative. We're going to cancel the 4. So let's write it x to the power of 0.6, y to the power of negative 0.6 over 15. Now, in these two new equations, you have lambda equals the first expression, lambda equals the second expression. So we can conclude that the two quantities here are equal. And of course, we can cancel the minus sign. So we can conclude here that x to the power of negative 0.4 times y to the power of 0.4 over 5 equals x to the power of 0.6 times y to the power of negative 0.6 over 15. And of course, you can cancel the 5 here and the 5 here, and it remains 3. So we can write that x to the power of negative 0.4 times y to the power of 0.4 equals x to the power of 0.6 times y to the power of negative 0.6 over 3. Now I will group the similar quantities, which are the x's and the y's, okay? So I will move this x to the power of negative 0.4 to the right side, and I will move the y to the power of negative 0.6 to the left side, okay? Now, when you move a power, you invert its sign, okay? So you will get y to the power of 0.6, because you moved here the y to the power of negative 0.6 from right to left, so it becomes y to the power of 0.6 times y to the power of 0.4 equals x to the power of 0.6 times x to the power of 0.4 over 3, okay? Now, using the exponents rule, you add the exponents here, so you will get y to the power of 0.6 plus 0.4, which is 1, equals, same thing here for the x's, you will get x over 3, and you will get here a relationship between the y and the x. You will use it to solve the third equation, okay? So we'll use this relationship to solve the third equation, which is 30x plus 60y minus 300 thousandths equals 0. So let's replace the y by its expression, which is x over 3. So let's write the third equation and include this expression here. So we have from the third equation, we have 30x plus 60y minus 300 thousandths equals 0. If you substitute the y by its expression, you will get 30x plus 60 times x over 3. It means plus 20x equals 300 thousandths. Okay, which means that 50x equals 300,000, which means that x equals 6,000. So you're going to use 6,000 units of labor to maximize your production. And of course, you can compute the y. So the y will be equal to 6,000 over 3. It means 2,000 units of capital. Of course, the corresponding amounts in dollars will be respectively 180,000 because each unit of labor costs $30. So you multiply 6,000 by $30, you will get $180,000. And here you multiply by 60 since its unit of capital costs $60, so you will get $120,000 of capital. If you add the two amounts, you will get your total budget, which is $300,000. The second part of the question is find the maximum production. Of course, the maximum production will be N of X and Y, which were found here. So here the maximum production is equal to N of 6,000 for X, 2,000 for Y, and you can, of course, compute it and get your maximum production. Thank you for your attention, guys, and see you in the next videos.